Hi, in this lesson we'll focus on the two most common subsetting tasks in Polars, selecting columns and filtering rows. You'll see how Polars uses Polars columns inside select and filter, giving you clean, chainable and expressive code. We'll start with a small in-memory data frame to introduce expressions and column selection, then switch to our coffee sales data to practice filtering and combining conditions. By the end, you'll confidently write Polars queries that return new data frames without modifying the originals. The goal is to understand data frame select and expressions with Polars columns. We'll begin by creating a small data frame and demonstrating different ways to select columns. Let's select two columns in the pandas way. We use a list of column names inside the square brackets. This feels familiar if you know pandas, but in Polars it's just a quick shorthand, not the recommended style. It's sufficient for quick column pruning, but lacks further capabilities that Polars has to offer. So let's explore the power of contexts and expressions for column selection step by step. Here we call .select directly on the data frame and pass in column names. It's concise and readable, but still uses plain strings. It works with one or more column names as well. In the second example, we get to know Polars column expression, which is the actual recommended method to select columns. pl.col introduces expressions, Polars' declarative way to describe what to compute. It looks more verbose right now, but soon you'll see why it's powerful. In both ways, we access the same data as before. An expression is just a recipe. It doesn't hold data until it's evaluated in a context like select. When we execute the cell, we see the instructions but no data. It basically tells Polars that we're interested in the columns name and age. The expression finally executes inside the DataFrame.select context, and we end up with the same table again. Let's dive a bit deeper into column expressions. They can also match columns by pattern or type. For example, we can select columns by regex pattern. Here we retrieve all columns starting with the characters NA, and this can be useful when you work with prefixed or suffixed columns, for example. Or we retrieve all integer columns with a simple one-liner by presenting the Polars type. It supports all Polars D types and even multiple ones at once, which can be pretty handy. We have the first idea of the expression's power, and now it's time to deepen our understanding of the select context. We select the whole data frame with the Polars all util. This is syntactic sugar for the plain asterisk regex. And we get a new data frame. It's worth mentioning that the select context always returns a new data frame, leaving the original untouched. So let's quickly check it here. Expressions go beyond selecting. Here we declare a processing recipe to calculate the average age and append the .mean method to the expression. And now we bring it into action by using the .select context. Besides the average age, we also calculate the most frequent name by chaining mode. Both expressions aggregate to the same level and result in a new data frame with a single row. Inside contexts, expressions can select, modify, or add new columns. As for the participants column, that we create on the fly and broadcast a single value to the whole column. Lesson 3 is assigned inside the literal method. Or as for the corrected age, where we add 2 years to the age column. This is just a short glimpse on data transformations. We cover it in more depth in the next video. In this section, we started with exploring different paths for selecting columns, learned that DataFrame select offers more than column retrieval, and we can create new data frames, perform aggregations, or create new columns in one go. Now let's filter rows using expressions. Step by step, we will compose complex filters and switch to a more realistic dataset. We created a slightly different coffee sales dataset in the last lesson. Let's load it directly from disk. This notebook also includes a minimal data frame, so the lesson is self-contained and you have an idea what's in the data. You'll find both the notebook and data linked in the description on my GitHub. The dataset contains 4 columns showing the sales of a coffee shop franchise and 1,000 rows for the full dataset. Note that I only printed the head, that's why the shape is 8 by 4. It contains sold drinks and their price, as well as a timestamp and a city of the store. We'll start with a simple equality filter, keeping only rows where drink equals water. The output confirms that the slicing and the size shrinked to 202 rows for the new data frame, whereas the size of the original data set didn't change at all. The filter method returns a new data frame and does not change the source data frame in place. All standard comparison operators work, lesser and greater than, equal and not equal, and so on. They are all applied the same. Here we keep the rows for all cities other than Los Angeles with the inequality comparison. We can combine conditions using bitwise operators and or to answer more complex queries. For the combination, we need parentheses around each single condition. Here we get the sales from Berlin or New York and a price of less or equal than $3. Filters are also expressions and can be stored for reuse. They don't hold any data. A concise variable name also helps document the purpose of a complex filter. So let's filter the rows where the drink is water or espresso. Under the hood, the filter context executes the expressions row-wise and uses a Boolean mask for subsetting. Besides the standard comparisons, Polars also offers a bunch of built-in filters. We can chain actions like is_in, is_between, or is_null conveniently. Here we combine the water or espresso filter to focus on the cities New York and Austin only. Next we see the is_between filter that checks all prices if they are between $2 and $3. And that's just a basic version. Is_between can actually do a lot more. You can include or exclude the boundaries or even make the bounds depend on other columns. If you'd like to explore these advanced options for the built-in filters, check out the Polars user guide linked below. The last missing filter operator is not, because sometimes we want to get the opposite of a condition. To negate any filter, we use the tilde in front of our expression. Here it negates the composed water or espresso filter, where we now keep all rows with any drink other than water or espresso. Or we can use the tilde with built-in filters, for example, to get all rows where the city is not in New York or Austin. Because both filter and select return new data frames, we can chain them safely to express a clear data pipeline. Here we filter to a condition we built earlier and then immediately select just the columns we want to see. We see that the franchise has the same prices in Austin and New York for espresso and water. Chaining operations are handy and avoid declaring variables for each intermediary result. You'll do it all the time for composing expressions or processing pipelines. Great work! You've learned how to select columns, filter rows, and how Polars expressions make these operations powerful and composable. We introduced expressions such as Polars columns and Polars literal and used them in the selection and filter contexts. Key points to remember. pl.col creates a declarative column expression, .select subsets columns, .filter subsets rows. You can combine multiple conditions with and/or and negate with the tilde. Always use parentheses for this. Each operation returns a new data frame, so no in-place mutation, which makes chaining clean and safe. You also find a quick cheat sheet in the end of the notebook. Thanks for watching. If this helped, please like and subscribe. In the next module, we'll build on expressions and start creating and transforming columns. A natural next step toward full-featured data pipelines in Polars.